Today, gas turbine engines are to be found all over the world, powering all manner of things, along with the production of energy. It has been part of the aviation industry since the 1940s, and while the design has, over the intervening years, undergone radical changes, with continual improvements in size, performance and fuel efficiency, the basic theory of operation has remained largely unchanged. Before examining the components that make up a gas turbine engine, to better understand how it works, it's necessary to examine the theory behind this form of propulsion. All forms of jet propulsion rely upon the principle of reaction as described by the 18th century mathematician and natural philosopher Sir Isaac Newton, whose third law of motion was that for every action there is an equal and opposite reaction. It's not the escaping air that moves the balloon forward, but the pressure imbalance within the balloon that makes it move in the direction away from the stem. And by applying Newton's second law of motion, we can calculate that reaction force. Acceleration of a body is directly proportional to the mass of the body, or F equals ma. In jet engine calculations, the body referred to is the expelled gas. Acceleration is the change of velocity in 1 second, and mass is the mass flow in 1 second. Another contributor to the theory behind jet propulsion, also from the 18th century, was the Swiss physicist Daniel Bernoulli, who laid down the law governing the changes of pressure, temperature and velocity in a streamline flow of gas. This law states that the total energy, pressure energy, velocity or kinetic energy, and thermal energy of a fluid is constant during a streamline flow. At the same time, a change in density and temperature will take place, the amount of change being governed by the gas laws. Bernoulli's theorem relates to the laws governing gas. But what constitutes a gas? Gas may be considered as a collection of molecules in motion, each of which behaves as though it were a perfect elastic body. When a quantity of gas is contained in a closed vessel, the molecules travelling in all directions produce a continuous bombardment on the walls of the vessel, and it's the average force of this bombardment which manifests itself as a pressure of the gas on the walls. Since the molecules may be regarded as perfectly elastic bodies, there's no loss of energy when they return from the walls or from each other, so that their total movement remains constant if no outside influences are brought to bear. Which brings us to Robert Boyle, the 17th century physicist and chemist, who stated that if the temperature remains constant, the volume of a gas varies inversely with the pressure. Before moving on to the various categories of gas turbine engines, there's one more theory we should look at. Jacques-Alexandre César Charles, an 18th century French physicist, left us with Charles' law, which states that for a given mass of gas at constant pressure, the volume varies directly as the absolute temperature, or if the volume is constant, the pressure varies directly as temperature. It's important to understand that because the working fluid in a gas turbine moves continuously and at high speed, aerodynamics plays a central part in the design of the gas turbine engine. Very basically, we need only 3 components to make a turbine engine. A turbine to drive a compressor to compress the airflow, and a combustion chamber to burn the fuel and create the flow of hot gas. Everything else is refinement. Aircraft gas turbine engines are divided into 3 main categories. The turbojet engine, which gets its power from the reaction of a gas expelled rearwards. The turboprop and turboshaft engine, which uses most of its power output to drive a propeller or helicopter rotor system. The turbofan engine, which is similar to the turbojet engine but employs extra turbine stages to drive a fan. The fan accelerates air around the outside of the core engine and produces typically 75% of the total thrust. For equal thrust, the turbofan engine uses around 50% less fuel than the turbojet and is much quieter because its exhaust velocity is slowed down by the mixing of the exhaust gas and the cold air from the fan. They can be high bypass, low bypass with mixed exhaust, or rear fan, where the fan is an extension of the turbine. The bypass ratio is the ratio of air flowing through the fan compared with the air flowing through the core engine. High bypass is about 5:1, and low bypass is 1:1. Turboprop and turbofan engines are basically turbojet engines in which the combustion gases are more fully expanded in the turbine sections to develop more power than is needed to drive the compressor and accessories. This excess power is then used to drive either a propeller, in the case of a turboprop, or a multi-bladed ducted fan, in the case of a turbofan, to produce thrust. Although a turbofan engine is described as though it were a turbojet, its characteristics are determined by the bypass ratio, which, to recap, is the ratio of the mass of the cold air passing through the fan to the mass of the hot air passing through the burners and turbine section. Work produced by a gas turbine engine is in proportion to the amount of heat released internally, most of which comes from the burning of fuel, although some heat originates when air is compressed by the compressor. But, as we all know, temperature and heat, although related, are not one and the same. We directly measure the temperature of water or air using an ordinary thermometer. Heat, however, cannot be measured directly, but must be calculated from three known quantities. They are temperature, mass or weight, and specific heat. Through an internationally agreed arbitrary standard, changes in heat content can be accurately calculated using the English system of the British Thermal Unit, or BTU. 1 BTU is defined as the amount of heat required to raise the temperature of 1 pound of pure water 1 degree from 15 degrees Celsius or 59 degrees Fahrenheit. The specific heat of water under these conditions is arbitrarily fixed at 1. All other substances are related to pure water through the values of specific heat found for each substance by experiment. We may then define heat as that which causes a change in the temperature of a body. To help us further understand the difference between temperature and heat, let's look at two blocks of iron, one weighing 10 pounds and the other 1,000 pounds. Both are at the same temperature. The larger block, however, has 100 times the heat of the smaller because it has 100 times the mass. Using the analogy of the turbojet, imagine two engines, one using 10,000 pounds of fuel per hour and the other using 1,000 pounds per hour. Both engines are operating at the same turbine inlet temperature. However, the larger engine can do approximately 10 times the work of the smaller engine because 10 times more heat is released at the same temperature. We should be aware that both Fahrenheit and Celsius scales are in use in aviation and are often confused. For example, the Fahrenheit scale is used by engineers to calculate and describe engine performance. Temperature indicators on aircraft instrument panels, however, are all read in degrees Celsius or centigrade, which includes the temperature instruments of the aircraft's engines. The measure of heat generally used in the United States is the BTU. A turbojet-powered aircraft obtains thrust by accelerating air through the engine. It is the reaction to the rate of change of momentum of the mass of the air that propels the aircraft. Like a piston engine, there is induction, compression, ignition, expansion, and exhaust. Unlike a piston engine, the process is continuous. A feature of the gas turbine engine is the use throughout of convergency and divergency, the increase and decrease of velocity, pressure and temperature through the use of ducts. In a gas turbine engine, the air is drawn through the intake by a compressor, which is attached to the main shaft. At the end of the shaft, the turbine is attached. Air drawn through the intake by the compressor will increase in pressure and temperature as it passes through the compressor stage of the engine. However, the successive increases and decreases in velocity practically cancel each other out. Air leaves the compressor and passes to the diffuser, which converts the velocity energy to pressure energy. On leaving the diffuser, the air passes into the combustion chambers. Of the total mass of air passing to the combustion chambers, approximately 25%, known as primary air, enters the flame tubes through the flame tube orifice and is used for combustion. The remainder of the air passes along the outside of the flame tubes, entering through dilution holes in the side of the tubes, and is used for cooling. Each combustion chamber is equipped with a burner containing a swirl-type atomizer, and through the atomizer the fuel is injected under pressure by the fuel pump into the combustion chamber, where it mixes as fine droplets with the incoming primary air. The combustible mixture formed is ignited by the igniters in 2 or 3 of the combustion chambers, depending on the design of the engine. On completion of the starting cycle, the igniters are cut off. At this stage, we can say that we have light-up. From this point, combustion is continuous, and the pressure in the combustion chamber for a given fuel flow is constant. The residual or secondary air, which passes through the dilution holes into the flame tube, mixes with the main mass of burning gas and cools it sufficiently to permit it to pass through the turbine at a temperature within the safe limits of the turbine material. Within the combustion chamber, owing to the added heat energy of the fuel, the gas both rises in temperature and increases in volume. After passing through the combustion chambers, the hot gases enter the nozzle guide vanes, which direct them at increased velocity onto the turbine blades, causing the turbine disc to rotate, which in turn drives the compressor. Of the total energy, approximately 60% is used driving the compressor, so that there is a considerable drop in gas pressure and temperature across the turbine. The remaining 40% of the energy after driving the turbine and the compressor is used to form a high-speed jet, which has a substantial residual pressure. This jet passes into the exhaust cone to emerge close to atmospheric pressure at the orifice. The jet not only has kinetic energy owing to its velocity, but also has substantial heat energy. However, the heat energy is released to atmosphere and is consequently wasted. Before we look at thrust and propulsive efficiency, let's talk about the various kinds of efficiency. Thermal efficiency, which is the useful power generated, divided by the rate at which chemical energy is produced by burning the fuel. Mechanical efficiency, which is the useful power delivered, divided by the internal power generated. Propulsive efficiency, which is the work done in propelling the aircraft, divided by the work in accelerating the airflow to create thrust. Cycle efficiency, which is the ratio of useful work obtained divided by the useful work obtained from an engine with an ideal working cycle. We better understand the relative performance of different types of turbine when we understand thrust and propulsive efficiency. The force that propels an aircraft is known as thrust, and it is the amount of static thrust a jet engine produces by which it is rated, just as a piston engine aircraft is rated in horsepower. Thrust is a function of the altitude and airspeed of an aircraft and of the engine control setting. It is this thrust force that accelerates the aircraft and balances drag. Because thrust is equal to mass times acceleration, equal thrust can be obtained from a turbojet engine giving a large acceleration to a small mass of air, or from the propeller of a turboprop giving a small acceleration to a large mass of air. Using mass times acceleration, it can be seen that the thrust experienced by an aircraft depends on the mass of air passing through the propeller disc or jet pipe in unit time, and the rate at which its velocity is changed. As the density of the atmosphere decreases with an increase in altitude, so does the available thrust. The thrust of a gas turbine engine is directly proportional to the atmospheric density. From this we can interpret that thrust is not just that which comes out of the back of a gas turbine engine. Propulsive efficiency, as has already been stated, compares work done by the engine on the air mass with work done by the engine on the aircraft. Obviously, work is done only when a force or thrust moves the aircraft through a distance. Conversely, thrust does not work on a stationary aircraft. Thus, the propulsive efficiency of an engine is zero when stationary, but the thrust is at its highest. When thrust causes the aircraft to move, the engine does work on the aircraft, and the amount of work depends on the distance moved. At high speed, maximum propulsive efficiency can exceed 80%. As an aircraft moves through the air pressure builds up in front of it, an effect hardly noticeable at low speeds, but considerable pressure will build up in front of the aircraft as speed is increased. This increase in pressure becomes pronounced at speeds above approximately 250 knots and increases the mass flow through the engine. This is known as ram effect. Turbojet propulsive efficiency rises continuously with increasing speed. However, turboprop propulsive efficiency, although better than the turbojet initially, falls off between 350 to 400 knots. This is because of increased drag produced by shock waves at the propeller blade tips. A compromise between the turbojet and the turboprop is the turbofan. Its propulsive efficiency is good throughout its entire operating range and produces thrust similarly to a propeller. Because the fan is enclosed in a duct, shock wave problems at the fan blade tips are reduced. Returning to the matter of ram effect, which is simply the natural compression of air flowing into the engine as it flies through the atmosphere. Up to about 250 knots, thrust falls steadily, as we would expect from the decreasing acceleration given to the air. Above this speed, however, the ram effect is sufficient not only to halt the fall, but to reverse the trend, until at 500 knots the static value has been regained. The rate of rise of thrust decreases beyond Mach 1 as a result of the formation of shock waves in the entry duct, unless measures are taken to counter the effect of shock waves on or in the intake. Sadi Carnot, a French engineer, discovered the rule of thermodynamics that states, "The efficiency of converting heat into useful work depends on temperature differences." He might have added, "and the colder the better." If we go looking for the coldest air, we'll find it in the lower stratosphere above 33,000 feet, where the temperature is about minus 55 degrees Celsius. The efficiency of gas turbine engines improves as the difference between the intake temperature and the combustion temperature increases. Therefore, the colder the air in which the aircraft flies, the better the operating efficiency of its engines. The higher we go, the less dense the air, and, since gas turbine engines operating in rarefied air suffer from respiration problems, we should not fly 1 foot higher than is necessary. For long-distance travel, the tropopause, the boundary between the troposphere and the stratosphere, is where conditions are optimal, where the highest density consistent with the search for low outside temperatures is found. The relationship between temperature, density and altitude may be illustrated by the following example. An aircraft's weight decreases as it burns off fuel. As the wings do not change size, the wing loading decreases. If the aircraft remained at the same altitude so that the air density remained constant, the decreasing wing load would require the aircraft to slow down, and the efficiency of the gas turbine engine would suffer, as they do not perform optimally at lower RPMs. And so, as its weight decreases, the aircraft must find more rarefied air in order to maintain speed. When the weight of the aircraft decreases, so does the drag. Less drag means that the engines need to deliver less thrust. It doesn't matter that, as the cruising altitude increases, the engines breathe somewhat thinner air. A Boeing 747-400 on a transcontinental flight might start out cruising at an altitude of 30,000 feet and a weight of 380 tons. 13 hours later, its weight has decreased by 1/3 to 250 tons, and, in the meantime, it has climbed to an altitude where the air density is also 66% of its initial value at 40,000 feet. Each hour it must climb roughly 800 feet in order to compensate for the fuel burnt. Turboprop aircraft operate at much lower altitudes, but they too suffer from the effects of density and temperature. At sea level, the air is thicker, and therefore there is more torque. The higher you go, the indicated airspeed decreases and the air is thinner. Therefore, there is less torque, and less torque means less available thrust. A Dash 8 taking off from an airfield 12,000 feet above sea level, with an outside air temperature of minus 30 degrees Celsius, the engine torque will be 90%. But from the same airfield, were the temperature to climb to plus 30 degrees Celsius, the torque would be 63%. With helicopters, it's a little different. The degradation of performance of the power output of a basic gas turbine engine on a helicopter as a result of reduced density and increased temperatures is primarily a function of the degraded effects on the rotor disc rather than the engine. From all this, we must agree that density and temperature plays an important part in the operating efficiency of the gas turbine engine and the aerodynamics of the rotor. Before we look at the various components that go to make up a gas turbine engine, we need to know that engine designers today draw upon a multitude of combinations of compressors, stages of turbine, drive shafts, combustion chambers, in order to arrive at the optimum engine size, power output and performance. It's a mix and match for the job required. For example, the ubiquitous PT6, which has undergone a number of changes in its long life, has 3 or 4 stage axial, plus centrifugal compressors, an annular combustor, a single stage compressor turbine, and a single stage power turbine. The engine can rate between 500 to 1,650 horsepower. These are details that will be covered within a type rating course, but they serve to illustrate the combinative nature of the modern gas turbine engine. Most civilian aircraft fly at subsonic speeds, and they, unlike supersonic aircraft that require a center body or wedge-type converging intake duct, require a divergent intake duct to decelerate the free stream flow and increase the pressure. Perhaps we should commence by asking, Why have compressors? Because it allows us to introduce a greater weight of air into the engine. Without a compressor, the engine would act like a ramjet, unable to start from rest. The combustion chambers would resemble campfires, and airflow through the engine would be less than efficient. Power output would be reduced to a level that would render the engine useless. Other reasons for a compressor will become more apparent as we look closer at this very necessary component. Compressors, as the name implies, compress the air. They compress the air because power output is proportional to the mass or weight of the air consumed by the engine. In aviation, there are two basic types of compressor, the centrifugal and axial. The difference between the two types of compressor is in the compressor construction and the way they achieve their compression. In the centrifugal compressor, air enters the impeller at the hub, then flows outward through the impeller vanes. This type of compressor is commonly used on most modern turboprop or turbo shaft of under 1,000 horsepower. They are cheap, lightweight, compact, and can ingest dirt without suffering damage. Axial flow type compressors are better suited to high mass flow, where the air flows parallel to the compressor shaft. Some engine designs incorporate both types of compressors, where an axial flow compressor feeds a centrifugal compressor. Every compressor design is a compromise between achieving high performance over a narrow RPM band or moderate performance over a wide RPM band. Each ring of blades and its associated fixed stator vanes is called a stage, so that the air alternately passes between rotor blades and stator vanes. Without the stators, the air would just be driven round and round by the moving blades to no effect. Each stage makes the air a little more compressed and also a little hotter, and its volume is reduced. The main component of a centrifugal compressor is an impeller rotated at high speed by the turbine. Impellers may be manufactured from aluminium alloy, steel alloys, or titanium. Centrifugal action causes the air to flow radially outwards between the vanes. At the same time, the impeller rotation causes tangential flow. Pressure of the outflow air rises because of the diverging passages between the vanes. The air then passes through a diffuser where the velocity energy is converted into pressure energy. Velocity is reduced and the pressure increased. A rise in temperature results because the work carried out by the compressor in compressing air involves adiabatic heating. The main advantages of centrifugal compressors are smaller, lighter and cheaper than axial flow compressors of the same capacity and pressure ratio, reasonably efficient over a wide range of operating conditions and RPM, very robust and tolerant of foreign bodies such as stones, ice and birds. They are also less prone to stall and surge. The main disadvantages are less efficient than axial flow compressors, 80% versus 90%. A maximum pressure ratio is also limited. In the axial flow compressors, the airflow is, as the name implies, axial, that is, parallel to the axis of the engine. At each compressor stage, the air is accelerated by the rotating blades prior to entering the following ring of diffusing or stator vanes. In so doing, the compressor converts kinetic energy into static pressure energy. The changes to pressure and velocity of the air as it passes through an axial flow compressor are as follows. Pressure rises at both rotors and stators, but velocity rises due to the accelerating action of the rotor blades and then falls due to the diffusing action of the stator vanes. Each row of stators acts as a diffuser for converting into pressure the kinetic energy of the air leaving the preceding rotating rows of vanes. Rotor blades are cast or forged from aluminium, steel or titanium, depending on their operating temperature. Main advantages of axial flow compressors are more efficient than centrifugal compressors, 90% versus 80%, small frontal area for a given airflow, high ram efficiency, pressure ratio is readily increased by adding stages. Main disadvantages are high efficiency is achieved only over a narrow RPM range, heavy, expensive and complex, more prone to stall and less robust than centrifugal compressors. At the very exit of the compressor, a diffuser section within the engine adds the final touch to the compression process by again decreasing the velocity and increasing the static pressure just before the air enters the combustion section of the engine. The theory being that for a continuous flow process, that is, when under steady conditions the same amount of gas passes all points in a given time, the flow is led through a divergent passage which causes a drop in velocity with corresponding increase in pressure, density and temperature. Diffusers are made from aluminium alloy or steel, depending on operating temperatures. Compressor stall, which can affect engines on both fixed-wing aircraft and helicopters, occurs when compressor blades exceed the maximum permissible angle of attack over successive rows of rotor blades and stator vanes. Both the blades and the vanes are similar to aircraft wing aerofoils. Stalling occurs when the airflow breaks from the convex side of the compressor blade just behind the leading edge. Once stalled, the blades lose the ability to push air down the engine. Compressor stall can be caused by low air velocity resulting from reduced inlet airflow or by a transient condition during run-up to full compressor load. It can also be caused by an external condition, such as ingestion of a foreign body into the engine intake. Severe stall can lead to a momentary flow reversal through the entire compressor. This is known as surge and puts extreme load on compressor blades and shaft. Surges can occur in rapid succession, causing flame, vapour or smoke to appear at the exhaust or even at the inlet. It is also identified by severe vibration and a loud banging. Stall and surge can be minimised with the use of bleed valves. Gas turbine engines employ compressor bleed valves to protect the compressor against stalling and surging conditions. Simply put, a bleed valve discharges a portion of the compressor airflow into the turbine exhaust duct. They're typically fully open during engine startup and acceleration to rated speed, gradually closing as RPM builds up, and normally fully closed at high RPM. The function of the combustion chamber is to burn a mixture of air and fuel at a steady rate and produce a continuous steady stream of gas at a uniform temperature. The requirements of a combustion chamber are maximum combustion efficiency, acceptable temperatures, stable operation, even outlet temperature distribution, minimum pressure loss. The fuel is finally divided, or atomized, into a turbulent stream of air, the mixture then being vaporized and burnt. Because fuel drops burn on their outer surface, they must be small enough to ensure that combustion is completed within the combustion zone. Forcing fuel under high pressure through very fine holes within the spray nozzle ensures small droplets. The job of the burner is to inject fuel in a readily ignitable form into the flame tubes of the combustion chambers. There are a number of different types of burners in current use. The function of turbines is to extract energy from the gas stream and convert it to mechanical energy. Over 50% of the gas stream energy entering a turbine is lost as exhaust heat. Various engine types utilize the remaining energy as follows. Turbojets. Approximately 75% drives the compressor and 25% produces the thrust. Turbofans. Approximately 75% drives the compressor and 15 to 20% drives the fan to produce fan thrust, and the remaining 5 to 10% produces core engine thrust. Turboprops and turboshafts. Approximately 75% drives the compressor and 20% provides shaft horsepower. On turboprops, residual energy provides thrust, but on turboshafts it is lost. Most shaft drive turbines have several stages of blading in order to extract as much energy as possible. To produce the driving torque required, the turbine may have a number of stages. Each stage has a ring of fixed guide vanes and a row of moving blades or turbine rotors. The number of stages depends on whether the engine has one shaft or two, and on the amount of power required from the gas flow, as well as a number of other factors. In modern engine design, the trend is towards more rather than less stages in order to reduce the stage loading. Turbine stages may be designed as predominantly impulse or predominantly reaction. In a turbine stage where the blading is of the impulse type, a pressure drop occurs only in the convergent nozzle guide vane passages. The stream of high-velocity gas is directed at the rotor blades, where the passages are constant in area and there is no further pressure drop. In a reaction turbine, exactly the opposite takes place. The entire pressure drop takes place between the rotor blades, which have convergent passages. The nozzle guide vanes do no more than guide the flow to the rotors. The turbine is driven by the reaction force resulting from the accelerating gas through the convergent blade passages. Turbine blades are made from special alloys of mainly nickel, chromium, and iron. The primary components of the turbine are nozzle guide vanes, the turbine disc, and the turbine blade. Nozzle guide vanes do two things. They convert pressure energy into velocity energy, and they direct the gas onto the rotor blades at the correct angle of attack. The impact or reaction of high-velocity gas on the rotor blades produce the large rotational force that drives the turbine. For a continuous flow process, if the flow is led through a convergent passage, the velocity must increase and there will be a drop in static pressure, density and temperature. This is the expansion process. The turbine disc carries the turbine blades and transfers their rotational force to the turbine shaft. They must withstand high temperatures and the very high centrifugal forces of the turbine blades. They are air-cooled. The basic principle behind the free turbine is the same as that already mentioned. There are usually two shafts, one driving the low-pressure compressor or gearbox, and the other driving the high-pressure compressor. The rear turbine, normally called the low-pressure turbine, drives the low-pressure compressor at the front of the engine or the gearbox. The front turbine, normally called the high-pressure turbine, drives the high-pressure compressor. Helicopter turbine engines, which have been with us since the mid-1950s, all have free power turbines in which one turbine drives the compressor and a different turbine drives the output shaft connected to the helicopter gearbox. The only connection between the compressor turbine and the power turbine is the main stream of gas, so each can run at its own best speed. The gases from a gas turbine engine are passed into the atmosphere by an exhaust system. After leaving the turbine, the gases are directed at high velocity. and, in a turbojet aircraft, produce thrust. In a turboprop engine, almost all the energy is absorbed in driving the turbines, compressors and propellers. Likewise, the exhaust systems on helicopters are irrelevant to the energy output. The design of the exhaust system is, however, critical to the performance of turbojet and turbofan engines. Depending on the type of engine, the average temperatures of the exhaust gases entering the exhaust system are between 550 degrees Celsius and 850 degrees Celsius. Bypass and turboprop engines generally have cooler exhaust gas temperatures. Turbofan power plants have a cold nozzle and a hot nozzle. Their relative sizes must be accurately maintained to ensure the correct relationships between core thrust, fan RPM and high pressure spool RPM. Nozzle size also produces low specific fuel consumption over certain engine operating ranges. Thrust reversal is a means of reducing the landing run of an aircraft without use of wheel brakes or the use of a brake parachute. On a pure jet or turbofan, the only simple way to slow the aircraft down quickly is to redirect the exhaust gas stream, thus using the engine power as a deceleration force. Over the years, such have been the advances in the design and the very nature of the gas turbine that it is impossible to predict how it will evolve in the future. That the aircraft, ships, and electricity generating plants of tomorrow will be powered by gas turbine engines is a given, but we can only speculate as to their design and power output.